There's just a tremendous number of jobs. And so, and you don't have to do the kind of job you did already. You know, the things, just if you can relax about it, it's not that bad. I know it's hard. It's easy to say this and hard to do it. So I have to wear a night guard because sometimes I get so stressed I grind my teeth, right? So, you know, I understand about this, but anyway. Seriously. So don't worry, you'll find a job. All right, so I'm going to talk about some more about combustion chemistry. Let's give a quick review of what we've talked about so far. So we talked about the general problem that society faces, that we're using fuels on a huge scale. They provide tremendous benefits to society. We want to use more because there's more people who'd like to have transportation and electricity. But if we do use more, we also have to cope with the environmental impacts of using more. And that doesn't look too good. So we're in a tough situation. People are thinking many different possible solutions to this, but one certainly obvious thing to try is to try to understand how the fuels work. First of all, if we understand how the fuels work very well, maybe we can design better ways to burn them in the engines if we had a very good simulations of what the fuel chemistry was. Secondly, if we have some idea for some future fuel that maybe doesn't hurt the environment as much as our current fuels do, then maybe we can assess whether it's a good idea before we go to all the trouble of building a factory to manufacture this fuel and then trying to do it experimentally. So we'd really like to be able to have this capability to predict the fuel chemistry. So that led us into a big discussion about how we could possibly do this. The chemistry models for the fuels we have now are very complicated, involving a very large number of species and reactions. So typically, fuels that are modeled, if you read the literature, models now have something like from 50 to maybe 5,000 chemical species in the models. And we have maybe 100 up to 30,000 reactions in the models. And so it's a large number of parameters in these models, lots of rate coefficients, lots of enthalpies of formation and heat capacities and entropies of all these species. And so we have to figure out how the heck we would possibly do this. So we decided first let's try to work in the thermochemistry. We want to be able to predict the thermochemistry of all the molecules that we think are important in our fuel. And this will be very important for determining the equilibria and also the heat release. And because the heat release controls the temperature, it's very important to actually have the enthalpies very accurately and the heat capacity too, because small changes in temperature change the rates a lot for reactions. And then secondly, we have to be able to predict the rate coefficients for all these reactions, which there's many, many, many rate coefficients. Half of them we get for free because we have the thermochemistry, because we can use that relation that K forward over K reverse is equal to Kc, and Kc is related to delta G. So we can, if we know the free energies of all the species, we can then compute the reverse reactions of all the reactions, all the reverse rate coefficients. But we still have to compute the forward rate coefficients, and that's a lot of numbers. And they're not just numbers, they're actually functions or functions of temperature and sometimes pressure. All right, so the thermochemistry, since we decided to do that first, there's some species thermo that's measured experimentally, and it's possible to do this very accurately. And so, for example, the Active Thermochemical Tables project has demonstrated how accurate you can do this, and it's just tremendous. But it's a lot of work, and as a consequence of the amount of work involved, people haven't done the work for a lot of the molecules yet. And so there's many molecules that we don't have experimental thermo numbers for. But there's also a set of a couple hundred molecules where we have tremendously good thermo numbers to maybe 5 significant figures kind of numbers. And so for those give very great benchmarks for any method we have for calculating thermochemistry because we can compare to those really well-known experimental numbers. We can do very quick estimates of thermochemistry from group additivity methods. And the group values originally were derived from the experiments and then more recently extended with quantum chemistry. However, this method is known to have problems with cyclic species and there's certain other kinds of molecules where it's known to not be very accurate. So we use the group additivity method a lot. So in my own research, maybe 90% of the thermochemistry numbers we use are from group additivity. but we're aware that it's not that perfect, and so we would really prefer if somebody would make the measurements, but the measurement guys seem awfully lazy. They don't seem to get them done as fast as I want. So we have to figure out some other way. So let's say maybe we can do it with quantum chemistry. Now the quantum chemistry, computing the entropies and the heat capacities only requires the geometry and the second derivative of the potential surface at the equilibrium geometry. And so typically we would compute this using the DFT method. The DFT methods are inexpensive. So you can actually do this for almost any molecule you want. You can do this calculation. And it's not really hard at all. It's like, you know, one day on a PC to do a calculation for your molecule. So even if you have 1,000 molecules, it's only 1,000 days. And actually maybe you have, you know, more processors than just one. So this is actually very feasible. So we've actually automated, and we can calculate thousands of molecules, entropies and heat capacities quite straightforwardly. And usually people use the rigid rotor harmonic oscillator stat-mech equations that I showed earlier. There's equations for the Qs and then the relationships between the thermochemical values and the Qs. However, this is known to have trouble with coupled torsions. So if you have a molecule that has several internal rotors and they're coupled together, then this has problems. But there's a lot of molecules that are not like that. So it works pretty well for lots of molecules. But when you do have that case, so for example, if you have a long molecule that has two polar functional groups that can form an internal hydrogen bond, then you're in trouble. But a lot of hydrocarbons don't only have one polar group or no polar groups. And the other groups more or less act as sort of hard spheres with respect to each other, and they don't really affect each other. And so it's fine. But now we want not just the entropy and the heat capacity, but we also want the enthalpy. And the enthalpy is a lot more trouble. And basically what we have to do is do the very best single point calculation of the energy, of the electronic energy that we can at the equilibrium geometry. That's the critical thing, is to know this number. However, even with the best method we can afford, oftentimes this is not accurate enough. So we need to know the enthalpy very accurately, down to sort of kilojoule per mole level. And most of the methods are more like error bars of 10 kilojoules per mole. So I'll show you in a second. So what's usually done is bond additivity corrections. So they go back to these really high accuracy values, and they use those small number of molecules where it's really accurately known. And they notice that the theoretical methods always systematically mispredict molecules that, for example, have a CC double bond in them. All molecules with CC double bonds are systematically off by like 1 kilojoule per mole. If they have two CC double bonds, they're off by 2 kilojoules per mole. So that makes them think, maybe it's just I need a correction, a fudge factor. Something's wrong with the quantum method. It doesn't compute double bonds correctly. And so they've made these fudge factors called bond additivity corrections. And this shows why they did it. So the orange lines here, each of these is a number of molecules that have an error of a certain size. And the x-axis here is the error between the true thermochemistry from the active thermochemical tables, very high accuracy thermochemistry, minus the quantum calculation. And these are 4 different quantum mechanical methods of calculating enthalpies. So this method right here is very widely used. It's very cheap. It's also very inaccurate. So you can see that the deviations, let's see, each tick mark here is 2 kcals per mole. So the median deviation for DFT is like 4 kcals per mole off enthalpy. Now, if you think of how big 4 kcals per mole is, what's going to happen is in all our populations and equilibrium constants, the enthalpy is going to be in the exponent. So you have your error in your enthalpy divided by RT. This is the magnitude. So if my error here is about 4 kcals per mole, and suppose my temperature is 1,000 Kelvin, might be kind of normal temperature for a combustion problem, and R is 2 calories per mole Kelvin. Is that right? So this is E to the, actually I shouldn't have a minus here, go to the magnitude. E to the 4,000 over 2,000. So it's E squared. So it's about a factor of 10. So I mean, all my, if I use this enthalpy, all my equilibrium constants will be off by about a factor of 10. but it's 10 plus or minus the range here, so I don't know. It might be a factor of 100. It might be a factor of 1. I don't know. So I have an uncertainty factor of 10. That means that all my reverse rate coefficients will also be off by a factor of 10 because of this problem. So this is too big. This is unacceptable for the models because it's not just one rate coefficient. It's everything. Half the rate coefficients in my model are all going to be off by factors of 10. And so that means that probably the rate limiting step will be off by about a factor of 10 too, just by Murphy's law. And so then I'll be a factor of 10 off all my predictions. So that'd be very annoying. So to try to deal with this, people can do the bond additivity corrections where they recalibrate the DFT method using the high accuracy experimental numbers, and that reduces the error a lot. And now the median is close to 0, and the variance is about 2 kilocalories per mole. So now you're only off by a factor of E, about a factor of 3. Okay, so this is very important to do the bond additivity corrections. But even with the bond additivity corrections, some molecules are off by 2, 4, 6 kcals per mole. You see some of them, these blue ticks are out in the wings here. So you could still be pretty significantly in error with DFT. So I would highly recommend you never use DFT unless you desperately have to compute an enthalpy, because who knows what your accuracy will be. And this is actually a very important problem for catalysis, heterogeneous catalysis, because for technical reasons, it's much easier to do density functional theory calculations for heterogeneous catalysis than it is to do anything else. And almost all heterogeneous catalysis problems are calculated using density functional theory, but all of them, therefore, have this kind of problem. And unfortunately, for the metal bonds, there aren't so many good experimental numbers to do the calibrations, so they don't even have the bond additivity corrections for many metal bonds to things. So you don't have any way to correct it. So you have variances like this in the catalysis calculations. So currently, the catalysis chemistry calculations of kinetics are semi-quantitative or qualitative. They're not quantitative at all because of the thermochemistry problem. Okay, but for gas phase, it's better because we do have the bond additivity corrections, but it's still really not good enough. So I would recommend don't use this method for the enthalpy. For the entropy and the heat capacity, this is actually very widely used, and it's not so bad. Because it's very cheap, it's really easy. Anybody can do it. I have my first year class, the third week of class, we had them do homework and do this. It's no big deal. You don't have to know anything. All right, so then the next thing that people did was they found out that this was not good enough. So then they used this method. It's called CBS-QB3. Now what this is a combination of several different types of calculations that are sort of in sequential order of accuracy. So you do an inaccurate calculation, a more accurate one, an even more accurate one. And then they were able to figure out for this sequence of calculations what the extrapolation formula is, so how the scales. And by following those scaling relations, they could extrapolate to an infinite calculation that should be perfectly accurate. So that's called the CBS, complete basis set limit. And Q, I can't explain to you what that is. The B3 is actually, they use the B3 lip geometries and frequencies because those aren't so bad. And it's just for the energy to get the enthalpy, the absolute energy, that they use this fancy method. And this actually drastically reduces the error. So you see this is the error, the orange, and now you can see how much tighter it is. So the CBS-QB3 is a much, much better method than the DFT. And then when you put the bond additivity corrections, it's really good. So you can see that now we only have like one molecule that's more than 2 kcals per mole in error, and most of them are less than 1 kcal per mole in error. So now you're getting accuracies that you can really be happy with. So this method, CBS-QB3, I think is used for most of the enthalpies in kinetic models that are from like the 2000s, since this century, in this century. This has been the workhorse method, really popular. A lot of people use this method to get enthalpies. And many, many, many of the enthalpies you have. And my group used this a lot to then go back and derive group additivity values, which we can then use to predict molecules that no one has ever done experiments on. And that works pretty well because these methods are pretty close to the truth. In recent years, people invented even better methods. So these methods, the CCSD parentheses T F12. Let's see if I can try to explain what this is about. So when you're doing a calculation of the electrons, the first thing people did was called a mean field theory, where you just consider each electron moving in the average electric field caused by all the other electrons. So that's also called Hartree-Fock theory. Actually, a guy got the Nobel Prize for that. And that works pretty well. It gets like 90% of the electron-electron interaction energy correct. But you're still 10% in error. And there's a lot of electrons, so that turns out to be a pretty big amount of energy that you're in error. And the reason why you have an error is because the electrons don't move in the mean field of all the other electrons. This electron is actually pushing those guys too, so they all move out of the way and avoid each other. So people realized that, and then they tried to figure out, and it's called electron correlation, the fact that when this guy is orbiting around this electron, it's affecting the orbits of all the other electrons to try to keep them away from each other as best as possible. And that makes it more stable because electron repulsion is reduced because they're staying away from each other. So people invented these methods called coupled cluster methods, and this is it starts out looking like perturbation theory, where you're first adding the first correction because this electron's reacting with that one, and now we're doing, well, actually this pair of electrons is also interacting with another pair, and so on like that. So you can write down sort of a perturbation theory sequence, but then there's a very clever mathematical trick where you make it better than a perturbation theory. It actually goes to like all orders of perturbation theory for certain groups of the terms. So you can write the perturbation theory expansion, do a certain amount of work that would correspond to some low order of perturbation theory, but you can automatically get effects of the higher order terms. And it's because the whole equations are very simple because all electrons are exactly the same. So there's like a lot of symmetry in the equations that make it possible to do this. So that's what the CCSD is. And then very recently, people figured out a way to explicitly include the distance between every pair of electrons in the wave function in their basis set. So when they're doing the calculations, they make the function, the probability of the electron being here depends not only on its location and its distance from all the nuclei, but also it depends explicitly on the exact distance of it to every single other electron. And you might have 100 other electrons. This is a lot of terms. But they figured out a clever way to do it. And that's what this method does. And then in all these methods, you have, at some point, a basis set expansion. So you're trying to represent the real probability field of where the electrons can be, called the wave function. And you have to do that as a sum in terms of some basis functions that you know. And the bigger that sum is, the closer you get to completely accurate. So this is a certain size basis set, and this is the next biggest one. And you can see that the error here is even better than CBS-QB3 already, though it's a little bit asymmetric. It's not centered on 0. But when you go to by the time you get to this size, now you're actually really close to the truth without any corrections at all. So the orange curve already has very small errors from 0, all centered around 0. And when you make the bondivity corrections, you can get really sharp spikes that basically everything's exactly right. And so that's the reason why we want to use bondivity corrections, is you can get this kind of collapse of the width of the errors gets much smaller with the corrections. And also you can make it centered on 0 instead of being systematically high or low for all the enthalpies. Yep.
Could you say again what DFT does and why it's not accurate?
Yeah. OK, so maybe I should write a little bit on the board. So a long time ago, a guy named Schrodinger, he figured out that you could write the exact So he realized, Schrodinger a long time ago wrote down this equation and said, this is an eigenvalue equation that for particular positions of all the atoms, you can solve it and get the electron energy. But you don't know, all you know is this operator, the Hamiltonian operator. He told you what that is. You don't know the eigenvalue, and you don't know the eigenfunction. You have to figure out what it is. The sad thing is that this eigenfunction is a function of the positions of all the electrons. So in a normal sized molecule, you might have 100 electrons. So there's 300 coordinates. It's a 300 dimensional function. So this is kind of hard to solve. And so people expand this as a sum of the basis functions for each electron separately. So it's like a bunch of products of one electron at a time wave functions. So instead of having one function of 300 variables, you have a product of 100 functions, each of 3 variables. And that turns out to make it a lot simpler. But that neglects the correlations, because when you write it that way, so I write that psi is approximately function 1 of x1, y1, z1 times function 2 of x2, y2, z2 times function 3 of x3, y3, z3. That's more or less what they said, is let's approximate this function of all those variables as a product of smaller functions that are lower dimensionality. And that's the Hartree-Fock approximation, more or less. But you get a lot of error. And then if you want to, because this form does not allow that this function depend on the position of number 2, of where electron number 2 is. But actually, the probability of finding electron 1 in some place does depend on where electron 2 is. If it gets too close, you're not going to find electron 1 here because it's going to be repelled, it's going to be away. So this is not really the right form. So this is a problem. And so then people wrote it this way and it was wrong, so then they said, well, let's write it as a sum of a whole bunch of forms like this and just add a zillion of them together. And if you do that, you can actually get better. But this turns out to be very expensive. And so that was the main way. It's called wave function methods. And from the 1930s all the way up, even till now, people try to do this. And it's a lot of work. The advantage is you know the true equation. This is the real true equation. And all you have to figure out is how to solve it. OK, so it's just a numerics problem, really. Just a hard numerics problem. Now, a guy named Kohn, he figured out that there's another operator, I'll call it the energy operator, and it operates on just the electron density, x, y, z, where the electron density is defined to be the integral of the psi squared dx2, dy2, dz2, dxn electrons. So it's a lot of integrals, a lot of d's. So this function is a function of 300 variables, and there's another quantity called the electron density, which is the probability of finding any electron here. So this one has to do with the probability of finding electron 1 at this position, electron 2 at this position, electron n at this position, all simultaneously. This one says, I don't care which electron I find. I just want to know, if I just look at this spot, is there going to be an electron there? And that's what this thing is. So this thing is only a function of three dimensions, x, y, z. And so Kohn proved that there's an operator that does this. So you can change the problem to be a problem only involving a function of 3 variables instead of 300. So this is pretty good. So everybody's very happy, except nobody knows what this operator is. So he has an existence proof that the operator exists, and it's universal, so true for every molecule, but nobody knows what it is.
For every molecule as well?
There's just I don't know, actually, that's a good question, I don't know. There's one that works for all molecules, but nobody knows what it is. So that was like a math proof of no utility to engineers. Kind of curious that such a simple solution exists. There's a way to write these equations, but what the heck are you going to do with it? But then a guy named Becke, Axel Becke, in 1988, made an inspired guess of a functional, of an operator, and when he applies it, it actually gets pretty close to the true values. And so that was like, oh, wow, amazing. And he had one adjustable parameter in his functional form that he had, and he adjusted it to make the energy of neon atom exactly match its experimental energy. And with that, all the first row atoms immediately were really close to reality, to the real energies. And the molecules you'd make with first row atoms, like hydrogen, like hydrocarbons, carbon, oxygen, stuff like that. And so people were really excited. So this would led to density functional theory being very good. But the problem is there's like a true one that solves this, and instead we have an approximate one that's sort of guessed, and we'll solve this equation, and we'll get a V approximate. So we solve this problem. This problem is easy to solve, so DFT is cheap because it's only a function in 3 variables. We know how to do differential equations in 3 variables, right? It's PDE, no problem. And so there's no problem to solve this. We get these V approximates. But they have error in them because we don't know the difference between this one and the E true, the true function, which is unknown. It's known to exist, but no one knows what it is. So that's the situation for density functional theory. So since 1988, people have gone wild trying to come up with better and better approximate functionals. And there's a whole community that publishes papers about that. I publish some myself, and some other people publish a lot of papers of different functionals. And there's a whole alphabet soup of different names of all these different functionals. And there's a complicated story about why they think it should be more accurate than the previous functional and so on. There's a whole community that you can probably go to a conference and read a journal paper, a whole journal volume, all with discussion about how to guess what the approximate functional should be. And so we, as in the combustion community, we just use that. So those guys work on it. Once in a while, they say, we think this new functional is a lot better than all the previous ones. Let's use that instead. So things like MO6, MO8, if you see those are like the more recent ones that people think are pretty good. But even there, people are like, how do you know if it's really good? You don't know what the real one is, so how do you know? Anyway, so people do a lot of tests to try to figure out and prove that their new functional is actually good or not. And anyway, that's a whole thing. So that's the difference. So these methods, here, 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 they're all used based on the Schrodinger equation. So they sort of know what the real equation is. They just don't know how to solve it. And this one here is they don't know what the real equation is. They use some approximate equation, but they definitely know how to solve it. So that's your choice. And this one's cheap to solve. And then these ones are a little bit fancier because they took the form, and instead of just writing it this way as a sum, now they add a whole bunch of functions that are functions of the distance between x1, this atom, this electron, and this electron. So there's a whole bunch of extra terms in the wave function that they write. But because they write it that way, it turns out to be a lot closer to the real wave function. And so you get better accuracy. So that's why these ones are more accurate. All right. OK, so is this OK? Everything's good with this? Yeah.
So how does the perturbation theory predict the MP2 and MP4 level?
Not that well. Not that well. So the perturbation, like MP2, the second order perturbation theory is approximately similar accuracy to the DFT. But the DFT is much cheaper to compute, so almost everybody does DFT. There's a fancier version called CASPT2. I'll write this one down. This one's pretty good. This one is one where they start writing everything down this way, but with a kind of a limited range of number of terms in the sum. And they solve that, and then after that, then they do second order perturbation theory to correct for everything they left out. And that actually works pretty well. So this is another pretty popular method. Still very expensive, but compared to this, maybe not. I don't know. So anyway, this is one that's still competitive as a method. And you'll see some people use this method. Some people will use these methods. There's some discussion about which kinds of molecules each one is more accurate for. A lot of work on numerics to try to make the things solve faster because they take too long. So that's what quantum chemistry is about. Yeah.
How would you get to know these methods and their codes?
Yeah, so there's codes. So for example, these methods, many people would use the Gaussian program, which is a commercial program. And it's has had a lot of users. So it has a lot of, and it's commercial. So it has had many iterations of trying to make it easier to use and getting out bugs. And so it's a pretty good. So I'd say that that's the most popular one. But there are actually many other programs. There's a lot of programs that could do these calculations for you. And you could decide what you want to buy. There's a lot of other companies that sell them. There's some free ones. But I would say the biggest market share is this program called Gaussian that has these. These methods are in a couple programs. And the one I like the best is called MulPro. And that has a very good numerical implementation of these guys. So I think that's the most popular one right now for doing those methods. Now these methods are just like perturbation theory. They're just a method. You can write down the equations. They're long. The equations are really long. But you can just write them down. And so it's in a journal paper, and anybody can implement them. So there's like different numerical implementations, just like different CFD codes. You can write down the RANS equations, right? And a lot of people have them, and you can, several different companies would sell you RANS codes, right? That should get the same solution if they implemented them all correctly and did the numerics right. And it's the same here. And so they do cross comparisons between the different commercial programs and try to make sure they all get the same number for the same molecule, stuff like that. All right, so that's thermochemistry. Now, my point of this slide was to emphasize that the bond additivity corrections help you a lot in improving the accuracy. And we really need that a lot when we do rate coefficients, because the rate coefficient by conventional transition state theory depends on these Qs. The Qs depend on the same things that affect entropy and heat capacity. So it depends on second derivatives of the potential and the geometries by the same formulas that we used before for the ROHO StatMech formulas. And so this first part, which is really the A factor, the Arrhenius A factor we're calculating, notice it's not really a constant. It has some T dependence, but basically it's not that, it doesn't vary that fast with T. And then this part over here is essentially EA, the activation energy, more or less. And this thing is basically the same as calculating a difference in enthalpies or something. You have to calculate the difference in the energy at two different geometries on the potential surface. And you need this really accurate because this comes up in the exponent. And we have the same problems that we did for the enthalpy for this. So you'd really like to have corrections for this. Just to remind you that we had before you can write this K of T, which is if you assume that everything is thermalized. So this is good for like bimolecular reactions over a barrier. The two guys are sitting around having many, many collisions before they hit each other with enough energy to actually react. So almost always this would be the right expression to use for the K of T. However, you can have some other ones I'm going to talk about a little bit later today where you are not thermalized. And if you're not thermalized, then you need to know the K, how it depends on the energy, because you don't have a Boltzmann distribution of energies. And so you wouldn't have any T in the expression. See, this is the expression. These two are just the same thing. If you do Boltzmann average of this, you'll just get that. And I just remind you that these are pretty rigorous. So there's a very limited number of assumptions that go into these calculations. And you can tie them very closely to the exact quantum mechanical rate if you read some complicated papers by William Miller. And people have done the exact quantum calculations for a couple small molecule cases. And then they've done these calculations. And they're not exactly the same, but they're pretty close. And you can see it's almost the same thing. Basically, if you do the quantum mechanics, you just get slightly different Qs and slightly different Ns from the quantum mechanics than you would from this expression, which is sort of semi-classical. But this is really easy. So almost every rate you see in literature, if they can do it this way, they'll do it this way. And often when you do this, it's not really any problem in the theory. The whole problem is almost to do with how well you can calculate that one number, the barrier height, because that's the most important number to know. And so we can do the enthalpies really well, as I showed you. But the reason we can do it is because we have these bond additivity corrections. So this is, say, allyl radical. And if you calculate it using these different methods, I don't know which one this is, actually. But you take one of these methods, even CCSDT, pretty fancy. CCSDT F12A is a very fancy method, right? Or CBSQB3, very good methods. If you calculate it, you have a quite big bond additivity correction from here to here, okay? And so it's like 5 kcals per mole. And the same thing here when you do for the product allene plus H. It's quite a correction that you would do. Now the corrections are different because this one has one double bond and this one has two double bonds. And the correction is pretty big per double bond. So this difference is different than this one. And because of that, if I calculate the saddle point, the barrier height top, if I use this one correction or the other correction, I actually get different numbers, even though I'm using the same quantum method. So it's because the correction is different. And I don't know which bond additivity correction I should use, because the bond additivity corrections were derived from enthalpy numbers of stable molecules and not from barrier heights. So I really don't know what the correction should be at a barrier height. And so I get some extra error just because I don't know what bond additivity correction to add. And if I calculate the rate in this direction using the blue method I get a lower barrier than if I calculate it in this direction with the red method, a little bit different. So my rates would be different depending on which way I calculate it. This is hidden in many, many, many papers and many models. The people calculate it in whatever direction they're thinking about it at the time, and then they're not realized that it's not completely consistent with the reverse. So it's a small inconsistency, about less than 1 kcal per mole. So for this particular case, it turns out to be something like a 35% discrepancy in the rate, which is not huge, but it's another error. And so anyway, that's just the kind of thing to keep in mind. And so this is the sort of the frontiers of where this calculation of rate coefficients is that we can calculate the enthalpies really very well with the bond additivity corrections, but we always get extra errors when we calculate the rate. So first we have extra errors in the barrier heights. It turns out also that the quantum methods are not as good at the barriers as they are at the stable molecules because of technical reasons about the way they do the calculation. So already you have a bigger error, and then you don't know how to do the bond additivity correction, and so the error is even larger, and then it all comes in the exponent, so it makes you feel worse. But that's the status. Yeah.
Yesterday you mentioned that to get the rate, you only need to know the energy at 2 points.
Yeah.
But to calculate where the settle point is, don't you need to match each point to get energy accurate?
Yeah. So you only need to know the accurate number, right at the tip of the saddle point and right down here at the bottom.
But how do you know?
But to find the saddle point, I have to do I have to do maybe 5, 10, 15 points around here to try to hone in and find the real saddle point. And actually I have to do the same thing down here. I have to hone into the real equilibrium geometry, the most stable geometry. So I do typically several DFT calculations to find the best geometry, and then at that geometry I'll do the highest level single point calculation I can to try to get the energy at that point as close as possible.
So on this diagram, actually the settle point energy you calculate, and you just make a line between them.
Yeah, so I just calculate this saddle point energy, this energy here. I do the second derivative calculation here and here. I add the 0-point correction from the second derivative calculation using harmonic oscillator approximation here and here. And then I take the differences between the two of them, and that's the delta E0, which is the critical number I need. And I hope all those numbers are perfectly accurate. So my delta E0 will be perfectly accurate. Okay, so the conventional transition state theory method is really very good, and it's really good for the case where you have a bimolecular reaction over a single high barrier. So if you have a potential energy surface that looks like this, something like this, A plus B goes to C plus D. Here's my transition state. If I use conventional transition state theory, I can calculate this very accurately. And the error will be whatever my error is in the delta E0, which might be 2 kcals, I don't know, something on that order of magnitude. So maybe a factor of 10 in error from the uncertainty in the activation energy, and then maybe another factor of 2 or 3 from uncertainties in the calculation of the Qs. So that's how good I can do it these days, pretty routinely. So I can tell my students, go calculate this, and tomorrow they'll tell me that, and it'll be good to that error bar. 2 to 3 in the A factor, and also factor of 3 to 10 due to errors in the barrier height. It's kind of typical. And then if somebody spends a lot of time on it, maybe they can make the error, instead of being 2 or 3, they can make it a factor of 1.5 in the A factor, and maybe they can make the barrier a little bit smaller. So maybe it's 1 kcal instead, so maybe it's just a factor of 3 from the barrier, something like that. And sometimes you're lucky and you get partial cancellation, that the error in the barrier and the error in the A factor sort of partially cancel and everything's okay. Sometimes you have bad luck and it's not. Anyway, that's the normal situation. So for this kind of reaction, we're okay. But there's a lot of other potential surfaces that can happen that have different issues. So one is this kind of potential where there's no barrier. So I started from this, and it falls apart to break a bond. Maybe A goes to B plus C. And there's no barrier at all, so I don't know where to put my dividing surface. There's no saddle point. So then I don't know how to do the calculation right. So this is where people would do the guess different dividing surfaces and just try a lot of them and find which one gives the smallest rate. And if you get into that, I would highly recommend you read papers by Klippenstein He's the world expert on this, and he's invented a lot of methods to try to efficiently find good dividing surfaces. But anyway, it turns out to be quite an expensive calculation, typically. Then another ones are like this. I'll talk about this more in just a minute. And then you can have ones that they look like the regular case we just did, except it's one molecule, A goes to B. And I'll tell you, there's a special problem with this. I'll show you in a second. And then this one where you have two humps. So the reaction comes in and it goes over two humps. And actually, I'll show you one more that I hope I have time to talk about. And sometimes you have a reaction like this, where it comes in, there's a van der Waals complex, there's another barrier. So here's like A plus B, here's sort of AB van der Waals complex. And then here's sort of a saddle point. I don't know, I'll call it the transition state, but I'm not sure it really is. And then here's the product. Okay, and so this kind of thing, and this saddle point could either be above the asymptote or below. If the top of this barrier is below this one, we call it a submerged barrier, and it makes a special headache. So we'll talk about that one too. But let's start with a simple one. So let's do the simplest case, and I think maybe the simplest one is maybe this one here. So let's talk about that for a minute. So suppose I have a reaction of that type. So this is like a molecule is falling apart to make two molecules. And it's a kind of reaction, if I try to run it reverse, these guys come together. They don't just attract each other at long range. They actually repel. I have to go over some barrier to get here. So from the point of view of the transition state theory, this is OK because I can say the dividing surface is right there at the saddle point. It should be OK. I can calculate the rate in this direction. If I assume all those assumptions I said, I can calculate this really easily using the transition state theory formulas, right? A plus B. I'm just going up to so I just use this as a reactant. I use this as the saddle point. I just use the formulas. Should be OK. Everything's fine. However, if I do come in here, B plus C, if a molecule of B comes and it bumps into a molecule of C and they smash into each other with enough energy that they can get over the barrier, they hit and they make sort of the proto-A. It's a BC thing. But this thing will be vibrating like mad because they hit each other with so much energy to get over this barrier. That means the system has a huge amount of energy. So I'm really making a very excited state of A, very highly vibrationally excited. And it has so much energy, it's above this barrier. So one thing that this can do is just fall apart. And so this is a situation where this rate can easily be faster than the collision rate or the thermalization rate. So I don't have a temperature-dependent, a Boltzmann population of A's. Boltzmann population of A's would be down here, right? That's what Boltzmann population of A would look like. I don't have a Boltzmann population of A's. I have all my A's are up here with energies above the barrier. And so using I don't have a temperature now. You see what I mean? My A is not described by temperature. It has no population down here. It has all the population up there. And so now I have to figure out what to do. So this is a case where I want to use the K of E formula, which I just had on the previous slide, I think. Here we go. So that K of E formula is the one I want to use. And depending on the energy, the guys with higher energies will have higher rates. And that's because if you look at that formula, the N of E of the transition state, what is that? Let's see if I can say what that is. So here's my saddle point. Here it is. The N of E is that there's quantum states of the transition state. There's quantum states here. And the N of E is, if I have this much energy, N of E is how many of these states there are with energy less than that energy. So in this case, 1, 2, 3. There's 3 quantum states. So N of E would be 3. And then the rho of E that's in the denominator is how many states there are over here in the reactant. And it's the derivative of that. So rho of E is dN dE. And so because this is so far above the bottom of the well, as you go up, the states get closer and closer together. There's more and more quantum states. By the time you get up here, there might be 1 million per wave number, or 1 billion per kcal, just a tremendous number of states. The density of states is usually a very huge number for the reactant. But for the transition state, you're quite close to the top, to the zero of the energy for the transition state. And so there's only a couple quantum states. So that's why the rates can be kind of small. But as you go up in energy, this also gets more closely packed together because the N of E increases, the density of states increases as you go up. So the N of E increases very rapidly with energy as you get away from the top of the barrier. So there's only one quantum state right at the barrier, but then not very far up, there might be 1 million quantum states. So that's what the situation looks like. So that's why you get this case where you have a very slow rate here, and then faster, 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 really fast up there. And these guys up here are definitely not going to live long enough to have any collisions at all. So you form this A excited, and it's just going to blast apart and never actually be effective at doing the reaction, because B plus C reacted. They made the super high excited A, and it just immediately falls apart, and all you see is B plus C. You never see any A. Does that make sense? 1 picosecond later, it's gone. So how are we going to model that? Oops. Let's go. So now I'm going to go back to the slides that you guys have printed. All right, so this is what's called a single well problem, because we have one well, one minimum here, and we have one reaction. This is a single well, single reaction. And this was observed to have strange behavior a long time ago. And we'll talk about the different methods people have for this. First, a couple simple theories, and then the more exact theory. And this topic is pretty complicated. I'm not going to try to explain everything about it. I'm trying to just give you an idea of what it's about. And then if you really get into these calculations, you'll have to read the textbooks and participate in the community about this. There are some software you can buy that can do it, but it's a little bit complicated. So the idea, anyway, is that so A plus B, sorry, different notation. Oh, I lost the display. You know what? Actually, before we get started on this, maybe we should just take a break, and then we'll do pressure dependence after the break.